Alright, hi everyone, welcome to my YouTube channel City of Electrons, and in this video we are going to be talking about this 3 examples. Okay, but we'll just start with one. We'll do one in this video, another in the next video, and another in the next video, and that will be all for this playlist for now. Okay, so yeah, examples on induction, examples on 3-phase induction motor. Yeah, that's it. So we'll start with just the first example. Note that we are going to apply all we've learned so far. Okay, the theories, the formulas, the this and everything. Okay, most of it. Now here's the question. A 3-phase induction motor having a star connected rotor has an induced EMF of 80 volts when slip rings at standstill on open circuit. The motor has resistance and reactance per phase of 1 ohms and 4 ohms respectively. Calculate current per phase and power factor when slip rings are short circuited. That's a B. Slip rings are connected to star connected rheostat of 3 ohms per phase. Solution. First thing first, data collection. Now, from the question we have that the EMF, okay, rotor EMF is this from the question. Good, we have that. Then what do we have again? Check. We have the resistance per phase. It was stated resistance per phase is what? 1 ohms. Reactance per phase 4 ohms with respectively. Okay, so we have this. Good. Now the rheostat per phase, the rheostat is given as 3 ohms, so that's what we have here. So what are we asked to calculate? Current per phase and what? Power factor. These are the 2 things we are going to calculate. Look at it. The current per phase and then the power factor. These are what we are asked to calculate. So in the first case, we are told that the slip rings are short-circuited. So how do we look for current per phase and power factor? Let's start with the current per phase. Note that from Ohm's law, V equals what? IR. So that means I equals V over R. So in this case, the voltage here, we are taking it at the EMF in this case. Okay, the resistance in this case, impedance per phase. And we've said that impedance, when dealing with impedance, we know that it is the sum of the real parts, which is resistance, plus the imaginary parts, reactance. Okay, so all we have to do is to get the value of this, substitute it in, calculate for the value of this, bring it in, and we've gotten our current per phase. Are we together? So now let's find this one. Okay, but the EMF, rotor EMF per phase equals what? Rotor EMF over √3. Where are we getting this √3 from? What's happening? Now, this is what we have as our rotor EMF. But we are dealing with what? Star connected. Okay? And we already have a video where we said, talked about the different connections, star connected and delta connected. For star connected, the EMF or the voltage per phase is written as this. Voltage per phase is the voltage for the 3 lines, that's the 3-phase voltage divided by √3. Okay, so this is how you get your voltage per phase. Now, with that being said, we have our EMF as this. So our EMF per phase will be this. The EMF, 3-phase EMF divided by √3. That's what's going on here. Okay, and that's how we got this. So we've gotten what this guy is. Now what about this guy? So we'll come down here and say, like I said earlier, that it is the sum, not just sum, but when we need the modulus, when we need the magnitude rather, we'll do this, saying that this guy plus this guy, of course, square root. And we've done this, how to derive this guy, why we have it as this and this, why we have this expression. We've done this in previous videos. So yeah, now what is the r? R is what? 1, and x is what? 4. So you just substitute that in and you get what your impedance is. Okay, so thus we now substitute in value. This will now be what? E is what? This, we bring it here. Z is what? This, we bring it here. And then you get your current per phase, rotor current per phase. Then for your power factor per phase is what? Adjacent over what? Hypotenuse. Okay, power factor per phase. Power factor per phase. This is your adjacent, of course, adjacent, and hypotenuse, of course, and then opposite, of course. Now, when we note that power factor is cos phi, and cos is what? Adjacent over hypotenuse. Okay, and what do you have at your adjacent side? Note that this is for resistance, this is for reactance, and this is for your impedance. This is how they are. I think we've drawn something like this before in previous video. Guys, we've done a lot in previous videos. I think we've done a lot. So please check out previous videos, and this present video will be easy for you to, relate with or something like that. Okay, so since cos phi is what? Adjacent over hypotenuse. What is in the adjacent? This guy. So you have it here. What is in the hypotenuse? This guy. So you have it here. And this is what? In the equation is what? 1. So you have 1. This we've calculated as what? 4.1231. So you put that here and you get this. This is your what? Power factor. Answer done. Answer done. Answer. That's the answer. So for the B parts, slip ring are connected to a star connected rheostat of 3 ohms per phase. Okay, 3 ohms per phase. Now, saying that 3 ohms per phase, the only difference here is that our resistance will no longer be 1, but since it's connected to a rheostat, we are going to add it. We are going to add it. So 1 plus 3, that will give us 4. Now, when we calculate our impedance, here will be 4, no longer 1, but it will be 4. Of course, the reactance remains the same, and that will give us our new impedance, meaning our current per phase will change. So, because the impedance has changed, okay, so this will now be what? The EMF remains the same, EMF per phase remains the same. The impedance is now 5.65229, and this will now give us the result of our new current per phase. And of course, it will affect, that change will affect what? The power factor, because R is now what? 4. Impedance is now what? 5.6569, and this will give us our new power factor. Okay, so that's for example 1. So we'll just leave this at this, and in our next video we'll talk about example 2. So yeah, thanks a lot for watching. Like, share, subscribe, and I'll see you in the next video. Bye for now.